Hello, this is a video on the EAS chapter, electrophilic aromatic substitutions, where I'll cover the reaction mechanisms of benzene bromination and alkylation. Typically, when we use Br2 to brominate a benzene ring, we find that there's no reaction. But experimental data shows that adding a Lewis acid catalyst like FeBr3 allows the benzene ring to be brominated, and not only that, but aromaticity of the ring is conserved. This is the following mechanism of this reaction. First, we must prepare bromine so that it's a strong electrophile to be reacted with benzene. This is the following mechanism. On the dihalide, one of the bromines attacks your Lewis acid catalyst in order for us to form this complex. And then the electrons of this bromine bond break and go to this FeBr4, and we form Br plus from this plus FeBr4. Br plus will be our important electrophile, while FeBr4 minus will be an important base we'll cover later. Now that we've prepared a good electrophile, the reaction proceeds as follows. The pi bond will attack Br plus so that the benzene ring now adds bromine like such, and then the base we created, FeBr4 minus, that can also be just written as base, will deprotonate this H and add a pi bond here, such that this is the final product. EAS alkylation is also similar to the bromination mechanism, where we prepare a good electrophile from our Rx species, like such. And so, now with our good electrophile, we can have an attack, and our base, or in this case AlCl4 minus, can deprotonate this H, and the electrons go to form this pi bond, thereby re-aromatizing our ring and adding R groups. An important note to mention is that if our R group is able to rearrange its plus with hydride shifts or methite shifts, like so, it will do so. Thereby, the final product looking like such, where this would be our major product, and our unshifted carbocation alkylation would be our minor product. So this would be our minor product if the electrophile did not shift. Minor.